Hi, this is Professor Fernandez, and in this video we're going to talk about Module 1 in Lesson 14. The topic here is surfaces as vector-valued functions, and the first thing I want to do is remind you of where we first started talking about vector-valued functions in relation to curves. So the rough picture there was and I'll just do this in two-dimensional space just to get us reviewing that. So remember we had a curve there where we were trying to express it as the range of some vector valued function. And I'm just drawing here two vectors in that vector valued function, but certainly there are a whole bunch of other ones that hit the other points on this curve. And we came to think of the interval over which t varied from a to b as mapping into or creating the actual vector that defined the vector valued function. And then we thought of these points as being the ones that we plotted in our space and connected to create our curve. So in three-dimensional space, we call these curves space curves. So what's going to change here is that we're going to do the same process but with surfaces. So rather than having a interval in the x-axis or the t-axis from a to b that we choose a particular t value in, and then that generates an x of t, a y of t, which then generates a point. What we're going to do now is we are instead going to bump up the dimension. So you'll see that most of these parametric surfaces are choosing points from a two-dimensional space where u and v are the axes, and there might be some blob. Most of the time this will be a rectangle where we choose a point, a u comma v value, and then we are going to put that into parametric equations that depend on u and v, and then we are going to put those into a vector valued function that depends on those parametric equations. And we are going to use those three values created, the x, y, and z values, to then plot a point in space. And then, of course, as we go back and choose a different point over here, that generates another set of three values, which generates another vector valued function, and that we will plot as another point in space. And so I'm not plotting the vector valued functions here because, as with the space curve up here, we think of the range of the vector valued function as the actual curve itself. Here, similarly, we're going to think of the range of the vector valued function as the surface that is generated as we plot all of these points. And that surface will be parametrized. It will have curves on it that correspond to one of the parameters being constant, and then other curves on it that correspond to the other parameter being constant. Great, so we will see this in the examples that I will work through in a little bit. But first, let me go through the actual definition of a parametric surface. So this definition says, let r of uv be equal to this vector, where again, you notice here that we have two parameters, u and v, not just the t single parameter that we were working with before. So we are assuming this is a vector valued function where x, y, and z are two variable real valued functions with a common domain D. So we are going to suppose further that r of uv is not equal to r of xy for all points uv not equal to x, y, and d. What does that mean? That means that if I look in the uv plane and I look at my domain D, which is where I'm going to be picking uv points from to then generate my parametrized surface, I'm going to assume that if I pick a point, it is mapped by r of u comma v into some point on my surface, and then if I pick a different point, it is not also mapped onto the same point, right? So as long as 2 points are different in D, like these two that I drew over here, then they get mapped to different points on the surface. In other words, we don't want to repeat points on the surface and associate them with different points in the domain D. So that's this requirement. And then let's talk through these three things. So the range of R is called the parametric surface defined over D. So again, that's similar to the range of R of t being called the space curve. And R along with D is called the parametrization of the surface, okay? We call the parametrization smooth if RVU and RV are continuous, and if the cross product of these partial derivatives is not the zero vector on the interior of D. This is really a condition that I'm going to come back to once we start talking about surface area and surface integrals later in this lesson and in the next lesson. So I'm going to not say anything about this for now. And then the last one, the range of the vector value functions R of u sub 0 v, R of u v sub 0, where we assume all inputs to R, R, and D are called the grid curves. So I kind of alluded to that up here. Now, all this being said, this is a little hard to digest. There's a lot going on. This is a very nice web page to just get a sense of a little bit of what this looks like and just play around with a helicoid as it's parametrized, and it's an interactive applet. So I encourage you to visit that. But what I'm going to do is actually use CalcPlot 3D to show you what these concepts look like, and in the context of this example. So let's look at this example. It says sketch the surface defined by this vector valued function and then describe the grid curves, these two. Okay. So first thing that I'm going to do is I'm going to note here that if I write this in vector form, it's written using the standard basis vectors, but if I just think of this as 2 cosine of u, v, and 2 sine u, right? We don't have to do this, but I can pick out this portion, and this is x, and this is y, and then this is z. So in other words, I have x equals 2 cosine u, I have y equals v, and z equals 2 sine u. Now remember, in parametric curves we had something similar where sometimes we would have a parametric curve that looked like this, for example, and we would say, oh, this is x, this is y. And then to graph the space curve generated by this parametric curve, we tried to find a way to remove the parameter. And there really is no right or wrong way to remove the parameter. It really depends on the functional relationships. For something like this, we use the fact that cosine squared plus sine squared is 1 to see that the space curve generated by this R of t vector valued function would generate a circle of radius 1. So we are going to do something very similar in this context over here. Notice that x and z have cosines and sines in them. So if I do x squared plus z squared, I get 4 cosine squared u plus 4 sine squared u, and I can factor out the 4, and that is going to leave me with cosine squared plus sine squared, which is 1. So whatever surface this parametric function defines, I know that in the xz plane I get circles of radius 2. So that's going to be very useful in a minute when we visualize this. So what's not included here is y. And that's because y kind of plays a different role as far as this parameterization goes. Notice that y is just equal to v. So it is quite separate from what's going on in the xz plane. All right, so then I'm going to go over here and draw the surface that we get, and I'm going to do it in 2 different ways, or I'll do complementary graphs, I should say. The first one is I'm going to draw the UV space, and then next to it I'm going to draw the XYZ space. All right, so thinking back to the function itself, we see that u appears inside of sine and cosine. So there it is. So u is basically an angle. So I'm only going to draw u between 0 and 2 pi. V, on the other hand, appears as the y component. So, there's no restriction on v. So in principle, v can be as large as it wants or as small as it wants. So v can range all the way to infinity, all the way to negative infinity. So really, the region D over which u and v are defined here. So D is the set of u, v, such that u is between 0 and 2 pi, and v is any real number. So that's kind of this half plane here. So this kind of goes up and down forever. And then what happens? So, well, we just, how do we plot this in R3? We just figured out over here that x squared plus z squared is 4. So that's a circle of radius 2. And we also figured out that y equals v. So suppose I start with y equals v equals 0. Then I am on the xz plane over here. I'm on the xz plane. And on that plane, I would draw a circle of radius 2 centered at the origin. So that's exactly what I'm going to do here. I'm going to draw a circle of radius 2 centered at the origin. So picture that circle on the xz plane. Now suppose I move up to y equals v equals 1. Well, I still have a circle of radius 2 in the xz plane. So there we go. And then as I move up to y equals 2, I get the same thing. If I move backwards, right, I also get these circles. So, you might recognize this as the equation of a cylinder. So then I just fill in the dots here and I get my cylinder. So how do I think about how these curves relate to the grid curves? So let me think now about R of U1. So if I just calculate this R of U1, I'm going to go up to the function itself, and I'm going to substitute in V equals 1. So that puts me over there. So I have 2 cosine of U, 1, and then 2 sine of U. So again, this x and this z generates my circle of radius 2 at y equals 1. So that is this grid curve here, right? The second circle that I drew. And what does it look like over here? Well, I'm at y equals v equals 1. So I'm over here, right? And then that entire grid curve over here is generated by going around, from u equals 0 to u equals 2 pi on this line, right? So for example, u equals 0, v equals 1. Well, u equals 0, cosine of 0 is 1, so I'm at x equals 2, and u equals 0, so sine of 0 is 0, x equals 2, z equals 0. So I am over here. So this is the point that is mapped from the UV plane to this portion, to this part of the curve. So, excuse me, let me get back there. Great. And then you can see as I keep going this way, U is basically an angle measured counterclockwise from the x-axis. You can see that here. So I'm going that way. So long story short, this grid curve is literally this circle at y equals 1 of radius 2, traced out from the point 2, 1, 0, and then rotating this way, counterclockwise as measured from the positive x-axis. So then let's talk about this grid curve. So if we calculate this, this is r of 0, v. So I'm substituting in u equals 0 everywhere I see a u. So I get cosine of 0 is 1. So that's 2. And then v, I'm leaving it alone. And then back to here, if u equals 0, sine of 0 is 0. So I get 2v0. Okay, so what does this curve look like? Well, it always has x equals 2, always has z equals 0. So I am over here. This is x equals 2, z equals 0. And then v just is varying. So v here is the y value. So v is just varying. So it goes back and forth that way. So this grid curve is kind of like being on the cylinder. I'll draw a cylinder here. And then it's literally the line on the cylinder that is at x equals 2 and z equals 0. So that is what this grid curve represents. And then how would we see it over here in this plot in the UV domain? Well, so U is 0, so we are over here, right? And then V is whatever you'd like. So this is the line here that is mapping onto this portion of the cylinder in three-dimensional space. Great, so I'm going to switch over to CalcPlot 3D to show you all of that. So here I have plotted, let me turn on my cursor. Here I have plotted the function itself. You can see, you can do this in CalcPlot 3D. You can select here and then pick down here parametric surface, and that will pull up all of this where you can put in your surface. So I've put in the surface we're looking at. I've restricted U from 0 to 2 pi, and I've just, this is the default for the surface when it comes up, so I just left it. So I'm only showing you a part of the cylinder. But what I wanted to show you here is now, if we turn on the UV graph, you see U and V here. This is the domain. And again, we're going from 0 to 2 pi. We're only looking at a little slice in V, only from 0 to 3. And what I'm going to do now is show you, as we move around, how this generates these grid curves. So first of all, let's look at the grid curves that we had already generated before. So the grid curves we generated before were the ones where the y value, the v value, was 1. So I'm going to take this cursor and move it around this way, and you'll see that that's going to generate, go around the cylinder once. So it's going to generate that circle that we saw. So here is my dot. I'm going to move this around. So I start over here. There we are. This is the point x equals 2 and z equals 0, if I were able to get it exactly on that point. There we go. And then I'm going to now move along this y equals 1, and you see the blue dot on the right. It is going around the circle and then comes back to where we started. So that was the first grid curve that we plotted. The second one started at the origin and went up the y-axis, the v-axis. You can see on the right here that that is exactly the curve or the line that we got on the cylinder, just going forward from x equals 2 and z equals 0. And then you can, play similar games here. Let's look at the grid curve generated by v equals 2. That again is another circle, but this circle is at y equals 2. Similar thing over here, grid curve generated by v equals 3 is another circle, but it is the circle at y equals 3. So that's just a very quick overview, and I again encourage you to play around with that example in CalcPlot 3D. The last one I want to do is show you that we can also use parametric surfaces in non-Cartesian coordinates. So, everything we did here, u and v, we were mapping that domain over to x, y, z, and just trying to find relationships here in a Cartesian manner. But we can try all of this in a different coordinate system, like spherical coordinates. So this example says, express the sphere here as a parametric surface using spherical coordinates. So the first thing to remember is that when you see x squared plus y squared plus z squared in spherical coordinates, that is just rho squared. So the equation of the sphere in spherical coordinates here is rho equals r. So that is nice. And so if I want to, and actually let me do one thing, let's change this to capital R so we don't confuse it with the other R's that will pop up. So if I want to parametrize this surface now, I am looking for parameters, u and v. And because I'm asked to use spherical coordinates, my parameters u and v I can take to be theta and phi. I don't need the rho because rho is constant. So rho is not going to be changing. So I'm going to take as my parameters theta and phi. And what my parametrization is supposed to do is to take these parameters from, some domain, which we'll figure that out in a minute, in two-dimensional space, and take that parametrization and produce the actual surface that I'm trying to parametrize in three-dimensional space. So I'm trying to parametrize a sphere of radius r, So that is a little bit of a clue as to how these parameters, this parameterization is going to go. So what do? Well, the x I have to relate to rho, theta, and phi in spherical coordinates. You may remember the conversion here. So I have x equals rho sine phi times cosine theta. Y equals rho sine phi times sine theta. And then z is rho cosine of phi. So because we're parametrizing a sphere and rho is constant, I'm calling it here capital R, then I'm just going to put this in here. And then I get effectively my parametrization. So this is my R of theta comma phi. I just put all of these x, y, and z expressions into the parametrization. And there we go. So this is my parametrization. I'm dealing with angles. So this is now the place where I want to talk about the domain here, from which we are going to select theta and phi. So I'm dealing with angles, and these angles have their own ranges. So if I go back then, and I want to do this as theta on the x-axis and phi on the y-axis, remember that in spherical coordinates, theta ranges from 0 to 2 pi, and phi ranges from 0 to pi. So 0 to pi. So I have as my domain my region D, over which we are going to select the inputs to my parametrization. In this case, it's a rectangle. I can select any point here, and that will generate, for example, if I selected the point pi comma pi over 2, then I'm selecting theta equals pi and phi equals pi over 2. I'm putting it in here, and then I am plotting this vector to generate the parametrization. That can be a little hard to picture, so probably the easiest thing to realize is that if I go on the actual sphere itself, or actually I drew it over here, if I look at a line in my domain where theta is constant, like this one. So if theta equals pi, well, theta is measured from the positive x-axis. So if theta equals pi, I am over there. And then if phi is varying, as it is on this vertical line, then what I am getting is a varying phi. So what does that look like? Well, so if phi is 0, I am at the z-axis. And if phi is pi, I'm at the negative z-axis. So if theta is pi, I'm over there. And phi starts here and goes that way. So I would be like sweeping out this part of the sphere. And that would be the portion of the surface of the sphere that is mapped by this vertical line over here on the right-hand side. You can see that if I go back and do this again for theta equals 0 here, then I would start here, and then I would sweep out this portion of the sphere. So as I move this way in my region, I am sweeping out the sphere by doing these longitude lines. This gives me another way to think about latitude and longitude on the sphere using this parameterization. And if I did things the other way, what if I chose a line segment here where phi is constant and theta varies? Well, that's going to lead to latitude, because if phi is 0, then, well, let's not choose phi 0. That's a little hard to picture. Let's choose phi equals pi over 2. Then those are all points that are on the xy plane. And as theta varies over here, I am going around the sphere. Okay, so that's effectively the equator of the sphere. So phi equals pi over 2 generates the equator of the sphere. And then as I go up in phi, then I am going from latitude curves on the sphere to lower latitude to the equator, and then to lower still. So moving down toward the South Pole. Okay, so that is how grid curves here are generated from selecting particular u and v, in this case theta and phi combinations in the domain D. Great, so last thing I want to mention here is that a surface that has a special form, the usual one we've been dealing with, z equals f of x, y, can always be viewed as a parametric surface by choosing the parameters x and y for u and v. In that case, x is just u, and y is just v, and then z is f of x, y, so I put in my z here. So this may seem a little silly, but it is a completely legitimate way to parametrize a surface. And it makes a lot of sense. If your surface has the form z equals f of x, y, you wouldn't, for example, although you could, write this as u, v, and f of u, v. You could, but then you would end up kind of getting back here anyway, because you would say, oh, this is x, and this is y, and this is z, which equals f of x, comma, y, right? So even if you did everything in the uv form that we've been doing the parameterization in, it leads you essentially back to this parameterization. So the reason I wanted to point this out is because, as we saw here with the example of the sphere, you are free to choose the parameters involved in your parameterization. It might make sense to parametrize certain surfaces using particular coordinate systems or particular parameters. That certainly made sense here for the sphere to choose theta and phi. It makes sense for a surface already written in terms of x and y, z equals f of x, y. It makes sense to choose your parameters to be x and y themselves. If you are, not given the surface, or if you're just given the parameterization, then of course there's no reason to change u and v to something else. There might at some points be a reason to do that. X and z here are linked in a circular manner, but that's kind of part of the reason why the parameterization was given in terms of sines and cosines. Okay, so this has been a quick overview of how parametric surfaces arise, how they're defined, how we plot them. Again, I'm going back here because I want to mention that this little bit of the definition I have not delved into, because that will happen in the next couple of modules and certainly in the next lesson. So I will see you then.